I start this third meeting with discussing homework, and I begin with the extra exercise 2.3.3. It is not in the book, but it is in the file with the extra assignments and exercises, other additional file. This exercise is about, well, we've seen in chapter 1 that there were subjective probabilities. We've seen in chapter 2 that the case of objective probabilities, what happens if they are both existing? Are they the same? Can they be different? This exercise is about it and shows that they must be the same in great generality. First, part A. Which objective probability distribution is generated by those three prospects? We look at the first. The objective probability of S1 is 1 over 3. So this gives probability distribution 1 over 3 for 100, 2 over 3 probability of 0. Second one, the objective probability of state S2 is also 1 over 3. This again gives probability distribution 1/3, 100, 2/3, 0. The third one, same story. 1/3 probability 100, 2/3, 0. So they all generate that same probability distribution. Part B, what are the preferences between them? Well, in part A, we saw they all give the same objective probability distribution by the assumption of decision under risk, that one. The only thing that matters about prospect is the objective probability distribution that they generate. So they are identified in that manner. So they are surely indifferent. So answer to part B, these are indifferent. Note, by the way, that you cannot claim indifference on the basis of identical expected values, because it is true they have the same objective expected values, but nobody said that preference maximize those. Preference maximize subjective expected values based on P1, P2, P3, not P1 prime, P2 prime, P3 prime. So at this stage, you cannot use expected value maximization to argue that they are identical, that they are equivalent. You have to use the reasoning that I just did, using the assumption of decision-making under risk. Now we go to part C. What are P1, P2, and P3, the subjective probabilities? Well, we have seen in part B that these three prospects are equivalent, indifferent. That means preference do maximize subjective expected value. That means these have the same subjective expected values. The subjective expected value of the first is P1 times 100, or the second is P2 times 100, or the third is P3 times 100. Note that now I'm using the subjective probabilities, but it means that those must be the same. P1 times 100 is P2 times 100 is P3 times 100, means P1 is P2 is P3. They must add to 1, so they must all be 1/3. So part D, we can say, are they the same or different? Well, they are the same. Now we go to part E. Part E considers not 3 states of nature, but n states of nature, but again, the same objective probabilities for every state of nature. And now you are asked to prove out of yourself that subjective probabilities must be the same as objective under all those assumptions written there. And the reasoning follows the same pattern as we saw before. First, we look at gambles that give you 100 on a state as j, nothing otherwise. For j is 1 up to n. We see all of them generate the same objective probability distribution, 1 over n probability of 100, n minus 1 over n probability of 0. So by the assumption of decision-making under risk, these, because they all have the same objective probability distribution, they must all be indifferent. And then we know that the preference maximizes subjective expected value. The subjective expected values of those prospects are Pj times 100, and now Pj is a subjective probability. But because they are indifferent, all those expected values must be the same, so Pj times 100 must be the same for all j. That means that all the subjective probabilities of Pj must also be the same, so they must also be 1 over n. So we have proved now that all these states of nature have the same objective and subjective probabilities. This holds even more generally, because if I take any event, let's say it contains j states, that event has objective probability j over n. The sum of those single probabilities, 1 over n, j of them. But the same thing holds for subjective probabilities. It also has j elementary states with subjective probability j 1 over n. So every state that has objective probability J over n with J states, J elements, must also have subjective probability J over n. Therefore, every event has the same objective and subjective probability. Those are entirely identical. This claim can be derived in even greater generality. Whenever we have a state space that is sufficiently refined, say a continuum, we can do such reasonings ad infinitum, so to say. For instance, maybe if it's a very refined state space, we can partition it in, say, million equally likely events that all have probability 1 over million. Then same kind of reasoning, they must all have the same subjective probability 1 over million. Then in fact, every union of them containing J of them must have both objective and subjective probabilities J over million, so they are all the same. Now, there can be events with a probability J over million other than the ones that we constructed a moment ago, but it's also easy to see whenever two events have the same objective probability, they must have the same subjective probability, because the gamble 100 on one event and 100 on the other event, then is equivalent, indifferent, by the decision making on the risk assumption, then the subjective probabilities must be the same. So then, in that case, I'm now discussing all the events with an objective probability J over million must have that same subjective probability J over million. And in fact, then if it's the state space is refined enough, you can prove that all events with a rational objective probability must have the same rational subjective probability. Rational is now this mathematical concept, K over L, where K and L are natural numbers. It's not the decision theoretic concept. Anyway, but if all the events with rational objective probability have the same rational subjective probability, then by a little bit of monotonicity that I will not try to explain very much now, it can be seen that for all events, whatever the probability is, whatever real number, they must have the same objective and subjective probability. So if the state space is a continuum, by these kind of reasonings, it can be proved that all objective and subjective probabilities are entirely identical. So this holds in great generality. There's here a part F of this exercise. It says, we have been assuming expected value maximization, but can you speculate if the result would hold in greater generality? That's a bit difficult for you because we haven't seen theories more general other than expected value maximization yet. But still, maybe you can feel, in fact, what is called stochastic dominance. I'll be a bit informal now and not 100% clear, a bit vague, but quickly I will tell you the basic idea. The basic idea is that the moment you have a theory need not be expected value, but it only satisfies stochastic dominance, meaning the bigger probability of a good outcome is also always better than the small probability of a good outcome. That's already enough. Because if you reconsider the reasoning we did, we really use expected value maximization here in part C, that indifference of these three prospects implies that the subjective probabilities must be the same. Well, in fact, imagine that we have a theory that need not be expected value maximization, but we do have the moment, for instance, P1, the subjective probability of S1, is strictly greater than P2, the subjective probability of S2. That would mean this prospect gives a strictly bigger probability of the good outcome than that prospect. And every theory that says, stochastic dominance fact, that big probability of good outcome is preferred to a small probability of good outcome. Any theory like that already says it cannot be, then this one would be strictly preferred to that one, but we saw they are indifferent, so it cannot be. So any such theorem says that P1 and P2 must be the same. In fact, P1, P2, P3 must be the same, must be 1/3, and that's all we needed. So indeed, that objective and subjective probabilities must be the same hold in great generality. You can now see from this exercise that subjective probabilities are not so much deviations from objective probabilities, because almost always they agree if they exist. They are rather generalizations. Whenever objective probabilities exist, the subjective probabilities must be the same, but there are many situations in which no objective probabilities exist, but still subjective can. Subjective probabilities are generalizations of objective probabilities, not deviations. And with that, I finish my discussion of exercise 2.3.3. The other homework is to be continued.